So first we're going to talk about domains where everything works out really easily. And these are the simply connected domains. And this is one precise way to say that a domain has no holes. So we say a domain is simply connected if every loop in it is null homotopic. So that means it should mean that there's no holes, or at least if we had a hole in our domain, it's easy to come up with curves that are not null homotopic. They would just go around the hole. But if every loop is null homotopic, then you can also prove that it means that there are no holes in the sense that the complement of your domain in the Riemann sphere has only one connected component. But we'll talk about those equivalences later. It's important to have some easy examples in mind, I think. So let me say something about some easy or some domains where it's easy to show that it's simply connected. So a star-shaped domain let's see if I can draw a star-shaped domain. Here, this is star-shaped. A domain is star-shaped if there exists a point in the domain which you would think of sort of as a center in some way, such that every line segment from z0 to z, where z is in the domain, every one of these line segments is also in the domain. So if I pick up, here's my z0, and I pick a point in the domain, then this whole line segment has to be in the domain. And I guess the way I've drawn it, this is not quite star-shaped because of the way this bends here, but if I'd drawn it a little better, maybe it would work out. But convex domains are certainly star-shaped. Convex meaning if I have z0 and z1, just any 2 points in the domain, to be convex, you have to have, for any 2 points, the line segment between them is contained in the domain. Okay, but star-shaped domains are easily shown to be simply connected, and here's the little proof. So if it's star-shaped with respect to z0, then I can say take any loop in a star-shaped domain, then I can just write down a homotopy right here, phi of st, and this is a way of parameterizing the line segment from gamma of t to z0. And so for s equals 0, I'm just getting gamma, but for s equals 1, I'm just getting z0. And so you're taking, let's see if I can draw a reasonable star-shaped domain. Here's just a star. If I have z0 here and any kind of loop in here, well then I can shrink it to the point that it's star-shaped with respect to. Okay, and the complex plane minus the negative numbers is surprisingly star-shaped with respect to any number on the real line, because if I take a point here, the line segment containing it is still in there. So any sort of the plane minus array would always be star-shaped. Okay, and then here are some easy consequences you get for simply connected domains, assuming the theorem on homotopy invariance of line integrals for analytic functions. So let's assume we have a simply connected domain, and then we have an analytic function. Then for any loop in the domain, we have that the integral of f over that loop dz equals 0, well, that's just from, we already said that if it's simply connected, every loop is null homotopic, so then this integral has to be 0. So there's nothing to explain there. If I have two curves with the same starting points and the same ending points, then the integrals are the same. And that's just, well, we'll see it explained in a second. It's not too hard. And then the third thing we can point out is that if I fix a z0 inside of U and let gamma sub z be any curve in U from z0 to z, which, since the domain is connected, well, I can always find such a curve. But since it's simply connected, I can define this function f of z, which is this integral of f over gamma z. And this turns out to give an antiderivative of f on all of u. So the point is we get global antiderivatives on simply connected domains. Okay, so how do you prove this proposition? So as I already said, 1 is immediate. Item 2 up above, well, just look at if I have these two curves with the same starting point and same end point, then if I follow gamma 1 and then go backwards on gamma 2, I get a loop. And so integrating over this loop, I'll get 0, but integrating over that loop is just this difference of values. And then 3, I need to show that this function defined here using paths gives me an antiderivative of f on all of u. Well, first, capital F is well defined by 2 because it just depends on the endpoints now. And so why is it analytic and why is its derivative equal to little f? Well, I'm going to fix a z1 in the domain and then find a disk around z1 that fits in the domain. Let g be an antiderivative of f on this disk. Now, for any z in that disk, I'm going to look at capital F and try to compute its complex derivative if I can. So f of z can be computed by taking any path from z0 to z to z. So I could go from z0 to z1 and then follow a line segment from z1 to z. But I can break this up into these two integrals of f in both cases. The first one will just give me capital F at z1, which I'm fixing temporarily. And then this other one I can compute by using a difference of antiderivatives, which I said capital G was a local antiderivative. Okay, but this now has just dependence on z inside this disk, but being analytic is a local property, so I can compute the complex derivative of capital G, and this other stuff is constant because I've fixed z1. So the derivative of capital F is the derivative of capital G on this disk, which gives me little f. So capital F is not only analytic, but its derivative is little f. An important consequence of this is that on simply connected domains, non-vanishing analytic functions have global logarithms. So that means if I have an analytic function that is never 0 on a simply connected domain, then there exists an analytic function g such that f is the exponential of g. So we can prove this by looking at sort of tricks that we used to define logarithms before. F prime over f will be perfectly analytic on the whole domain because f is non-vanishing. And it has to have a global antiderivative by the previous proposition because we're on a simply connected domain. Okay, so we can, it's a global antiderivative. We can change it by a constant if we want to. So we can arrange for g of z naught to be a value of log of z naught for some fixed z naught. And now we just check that g does the right thing. So you take the derivative of f e to the minus g, you get f prime e to the minus g minus f e to the minus g g prime, but this was f prime over f. So the f's cancel and you just get 0. So this function is constant. So it's constant, so it equals its value at z naught, but we've arranged for this to be 1. So f is identically equal to e to the g. What we also get out of this is global square roots of non-vanishing functions. So on a simply connected domain, every non-vanishing function will have a global square root too, which I can just write it this way, e to the 1/2 g, and if I square this, I'll get e to the g, which is f. And that's all I wanted to say about simply connected domains, and now we will talk about Morera's theorem, which gives a characterization of analytic one-forms.